let's talk about bias and variance today. This is a very important topic for us to keep in mind whenever we are trying to look at the error matrix values from both train and test. Especially at the beginning of the stage when you are very new to machine learning and you're trying to apply different models, each model would show some kind of an error on your train data set and some kind of an error on the validation data set. So looking at those errors, we can draw some conclusions. To make those conclusions, we have to understand what is bias and what is variance. So let us look at each topic at a time. Before going to bias and variance, I just want to refresh around the complete cycle of machine learning. We start off with a business problem. We try to gather the information that is required to solve this business problem, and then we apply a lot of cleansing methods. Maybe deal with outliers, deal with null values, remove those columns which are not required, or maybe they don't change in any of the records. Maybe they have a constant value, and look at the some kind of a visualizations to see if there is any pattern that we want to analyze, and then try to divide the data into train and validation. Build the model with on the train, test the model on validation, see if the scores are similar, like the score of train and the score of validation, are they similar or nearby to each other or not, and then maybe deploy the model and predict on a general use case, and then keep monitoring the model. So just in case if the model is not performing well, then you have to redo the complete activity. The number of steps can vary based on, you can include more steps into it, but overall I think you can stick to this four or like 5 or 6 points that we have. I want to draw your attention towards this point number 4, where we try to divide the data in train and validation. So generally this happens at the point before we apply a model. So we divide the data into train and validation. We convert all the categorical columns to one hot encoding or label encoding. And for the numerical scales, maybe you apply a scalar, standard scalar or a min-max scalar to bring them to same scale. And then we allow the model to get trained. So now what the model will do, it will try to predict betas and beta knots, and then it will try to generalize it will come up with some kind of a normal way which can apply to all the complete data set. Okay, this is where we have to uh, emphasize more on what it is trying to tell us. Say, uh, for example, let us say that we have applied a model, and the model is trying to tell that on the train data set, I'm getting a RMSE, like the root mean square error of 5. The same error on the validation, I'm getting 15. So there is a lot of variation between my train error metric and the validation error metric. So when you have this difference, there are a couple of things we have to analyze and look at. So the first thing that we are going to look at is bias. Okay, just keep that in mind. Whatever we discuss, just keep that in mind. So we'll discuss something about bias. Now, let us say I have bias. Okay, let us say I have a car, and back in like in India, we have different kinds of petrol stations. Say, for example, I have Indian Oil, I have Bharat Petroleum, I have maybe Hindustan Petroleum also. Say, for example, I have 3 petrol stations. But since the time when I bought this car, I always go to Indian Oil. I don't know if there is any difference of purity in petrols of all these manufacturers. Probably you can, if you do not have a choice of Indian Oil, probably I would go to any of the petrol station, because if it is empty, then you have to run your car, right? Then because I don't have a choice, then I'll go to this. But on a general day, whenever I have to fill, I am inclined towards going to this petrol station than any other. Like this is also one kind of a bias. Maybe it is a positive bias, say for some kind of reason, like I don't want the engine to get spoiled with difference of petrols. Okay, this is one kind of a bias where you're inclined to one kind of a data rather than the other data. But for us, for the machine to work for any kind of a data, we have to generalize. I cannot tell that you look at only Indian Oil and based on the Indian Oil patterns, go and predict on Bharat Petroleum or Hindustan Petroleum. That's not going to work. All right, keep this in mind. So having said about that little example, when we have a simple model like linear regression, the base assumption of linear regression was to have a linear relationship. Let us say that I did not look at the relationship between my independent feature and dependent feature, and I still went and applied a linear regression. Now, what will linear regression do? It will still find out beta 1 and beta naught, and it will try to come up with some model. So it is trying to fit even when the data is not linear. Say, for example, you can notice that it is having some kind of a parabolic or maybe a U kind of a model here, but I'm trying to force the linear metric to go and find a linear relationship. So what it's trying to do, it is looking at only some kind of a data and it is trying to fit the line. It is avoiding all the black color dots. This is one kind of a bias. Okay. On the other hand, let us say I have a data frame and instead of shuffling the records, I took the top 80 as my train and the bottom 20 as my validation. Now, this red colored dots here is from the validation. The train was perfectly linear, but because I did not do a random sampling, my model is inclined towards this train dataset, and it is when it comes to test the validation, it miserably fails. This is one way. Or let us say that I have two features, x1 and x2. For some reason, I did not look at x2 at all, or maybe I did not look at x1 at all. I avoided it completely, and then I'm considering to build the model just on x2. Only this feature I'm going to consider. So it is going to look at the black dots and it is going to come up with some line. But what has happened, because y was also dependent on x1, it is inclined, now you're forcing the model to predict y only on x2. So it'll make errors. So model, you feed trash in, trash out. If you feed garbage, the garbage will come out. So if you want to model to perform very well, you need to make sure that the data set that you're considering is also good. And you're applying all these techniques, like you do a random sampling, you try to reduce the outliers, you try to see if there is a linear relationship or not, and then you go and apply models. Considering a case where we overlook one of the assumption, then we go and make this bias kind of a problem issue. Okay, how to reduce bias is by considering more number of features. So I have a features with x1 and x2. Even though if I consider two features, if my model is getting biased towards some kind of a data, try to see if you can find more features like x3 and x4 and all. So one way you're trying to increase the complexity. When I say increase the complexity, increase the number of features and then train the model. Okay, it need not be, I would not say that only linear regression has bias and variance. Almost all the machine learning models have this bias and variance. How to deal with it is what we are looking at. Okay, so if you want to reduce the bias, increase the complexity or increase the number of features or increase a complicated go and train with a complicated model. Now linear regression is a quite base model. That's a very weak learner. If you want to go with a non-linear model, probably then you have to go to decision trees or k nearest neighbor and so on. Like we did not discuss those models yet, but yeah, you will soon also look at those models. Okay, now let us go and understand what is variance. Now variance is a point where we have good performance on our train. Now let us say I have a model and my data was like this, and the model was trying to go to all the data points. Okay, and on my train, maybe I'm getting like 99 R square and very less RMSE, let us say 1, root mean square error is 1. So on the train, it is very good. But when I go and fetch an unseen data, the model makes a lot of mistake. So the R square which you saw on the train at 99, at the validation, you might see at 80 or maybe 70. far away from what this 99 was. This is like an overfitting. You wanted the model to generalize on all the data, but it is trying to find out, it is trying to find all the patterns. But you should not, as I said, like you should not learn all the patterns. You should learn some kind of a patterns and generalize. And it should not have too much of deviation with the slightest change in my dataset. Now, when I say a slightest change in dataset, what I mean is, if I have a trained data and I'm doing a k-fold cross validation, I divide my dataset into 3 halves. I keep this for my testing purpose. I train with these two data sets. And then similarly, for the second round, I keep this as my testing purpose. This I will keep for my train. And similarly for the third, I'll try to keep this on my validation, the rest two as my train. And for the 3 trials, trial 1, trial 2, and trial 3, I measure what is my error metric. Let us say I'm looking at RMSE. The RMSE in trial 1 was 10. In RMSE in trial 2 was 2. RMSE in trial 3 was 8. You notice that the errors were not constant. Here the error is 2 less, but here the errors are quite high as compared to this one. In order to have a very good model, when I go and do a k-fold cross validation, I need to make sure that all these errors are very close to each other. There is not too much of deviation from one error metric to another error metric. So how to solve variance? I don't want the model to go and find each and every pattern on the data. I don't want that model to do. So what should it be doing? You have to reduce the complexity here. In the case of bias, increase the complexity. In the case of variance, decrease the complexity. This is where you go and apply feature selection. Let us say I have like 10 features. The model is getting O of it. Instead of 10 features, I try and go and do with 7 features. I'm going to still hold all my previous learnings. I'm going to look at what is my correlation, what is my relationship of y and x, are they linearly related or not. I'm going to hold all these things. In addition to that, these are the new things that I'm going to look at. I'm going to look at what is my score in my train, what is my score in my validation. Based on this, I will decide if I have to go with 10 or if I have to go with 7. Okay, this is about variance. Now variance is more to do with overfitting. You don't want the data to learn all the patterns in the you don't want the model to learn all the patterns in the data set. You want only some kind of a generalization. It should look at all the variables and it has to try out to find out only those patterns which it can generalize. For a slightest change, it should not vary a lot of it should not vary too much in the error metric. All right, so if you want to go and look at how to visualize this, so this is how it would look. If my model is robust, it would have low variance and low bias. Low variance and low bias. So this is my center. I want the values to be clustered around the center. If the model doesn't have bias and it doesn't have variance, all the predictions are revolving around that center. Now, what would happen if it is high bias? When in the case of high bias, these are clustered but away from center. They're not at the center, they're away from the center. The variance is less. You can see the cluster, the dots are very near to each other. So the variance is less, but the bias is more. Similarly, if you have very high variance but low bias, it would have like it is around the center, but each prediction is far away from the center. It is pretty much scattered. This is pretty much clustered. You can see it is within that orange circle. But if you go and see, it is crossing the blue circle. Again, it is going to the next orange circle. And here is a case where you have high variance and high bias. Drifted away, not in the clustered form. They're away from the center. Pretty much scattered. High variance, high bias. So in order to find a model which is having low variance and low bias, we have to do some kind of a trade-off. As I said, if you want to reduce bias, increase the number of features. increase the number of features. But again, as you increase the number of features, there is a fear of increasing the variance also. So you should not increase too much. Like if you increase too much, then you'll end up having high variance. So that is a point where you need to have some kind of a sweet spot which has low variance and low bias. Now, how to do this is to have some kind of a trade-off. So as I said, we have model complexity. We are trying to increase the number of features. The bias will come down. The bias is coming down. On the other hand, when the bias is coming down, the variance might also increase. Okay, so we need to find some kind of a point where my bias is low and my variance is also low. So you try out with different combinations of models and come to this point. Of course, you don't have to do this manually. We have libraries for this. Say, for example, we did not go to a point where we try and speak about ensemble, but we have a model like random forest, which wherein you can pass like say any number of columns to it. Let us say I pass like 100 columns, and I'll ask random forest to make say 200 decision trees by randomly selecting like 20 features of this. So you're trying to consider 20 features, make one decision tree. You try to consider another 20 features, make one more decision tree, and so on. Like this, you'll build 200 features. So slowly, your whatever variance issue you had, it'll try to get reduced, and you'll try to find this point. That is about bias and variance. I hope I was clear around us. So if you have any doubts, just feel free to leave a comment, and then I can try to resolve this, or maybe I can revert back to you as soon as possible. Thank you for the session.